So now let's look at an important application of jackknife, which is leave one out cross-validation for model or variable selection. When you're fitting a regression model, and by regression model, I mean any model where you try to find out what is the conditional expectation of a dependent variable y given some set of independent variables x. So the model can be linear or nonlinear, and your y can be continuous or categorical. So when you fit this kind of models, then you might want to evaluate the out-of-sample performance. For example, the out-of-sample mean square error. And this can give us an idea on the prediction accuracy of the model for new observations. One way to do this is to split your data into, say, a training set, which you use to fit the model, say 70% of the data, and then setting aside a validation or a test set where you fit the trained model and see how well the trained model performs. However, the data is sometimes scarce, and in these cases, we cannot afford setting aside separate validation or test sets when training a classifier or fitting a regression. In these cases, an alternative to setting aside a test set is using cross-validation. In k-fold cross-validation, we partition our dataset into k subsets. For each fold, so for each time, we fit the model on all data except the k subset. And then we evaluate the performance of the model on the k subset. When k, which is the number of folds, is equal to your sample size n, then each subset is one observation. In that case, what you're doing is fitting a model excluding that observation and predicting the observation and trying to do validation. And this is known as LOCV, leave one out cross-validation. This is very commonly used in statistical and machine learning for variable selection or choosing a good model. However, as a statistician, you should know that the cross-validation, specifically LOCV, is not something exclusive to data miners. It is actually also used for variable selection in regressions, for example, our linear regression models. If you have taken 425, then you might have learned one of the variable selection methods, which is the use of the AIC. So it turns out that the AIC is asymptotically equivalent to LOCV. In other words, asymptotically, choosing the model that minimizes AIC is equivalent to choosing a model that minimizes the leave one out cross-validation error. If you're interested in this, then you can check out the link that I included here, which is an article that discusses the relationship between AIC and leave one out cross-validations. We're going to see an example of this using the iron slack data in R. So we are going to use LOCV to select a model that can fit the data the best. The iron slack dataset is a dataset on iron content measurements. Two methods for measuring the iron content in samples of slag were compared, a chemical method and a magnetic method. This dataset is available in the doc R package. If you haven't installed it before, you will need to run install.packages doc, and then you'll be able to load this dataset inside this package. This dataset, called iron slag, contains 53 observations on two variables. The first variable is called chemical, which is a numeric vector containing the measurements coming from the chemical method. The other variable is called magnetic, which is another numeric vector containing the measurements coming from the magnetic method. Our purpose is to predict the magnetic measurement, which we will denote by y. That's our dependent variable, from the chemical measurement, which we denote by x. So one question you might think about is, what are some possible models for predicting y from x? If you take 425, you will learn about all of the possible models for doing this. But here, let's just present 4 possibilities. These are the 4 that are listed on the book. The first is the linear model, the simple linear regression model, where y is equal to beta 0 and intercept plus beta 1 is slope times x plus e, the error term. The second is a quadratic model where we include an additional quadratic term, x squared. The third is an exponential model where we transform our y's first and then do a linear model. So log of y in this case is equal to some intercept plus beta 1 times x plus e. It's called the exponential model because if you take the exponential or exponent of this, then you get y is equal to beta 0 times e to the beta 1x plus something. The fourth possibility is we transform both our y and our x. In this case, log of y is given by beta 0 plus beta 1 times log of x plus e. So these models can be fitted using the R function Lm, which stands for linear model. We're going to fit each of these 4 models using Lm and R and plot the fitted curves on the scatter plots of x and y. Here's a code for fitting the linear regression models on for each of these possibilities. L1, L2, L3, and L4 stands for the linear models with these 4 different forms. The attach iron slag line over here essentially attaches the iron slag dataset into our R environment. So by doing this, we won't need to type iron slag $ magnetic, iron slag $ chemical every time we use these variables. So here's the code for plotting the fitted curves. I will just discuss this for the first case, so the linear model, and you can look at the rest yourself. What we do first is to create a sequence A of possible x values, again using the sec function. And then par mf row equals C22 tells us that we're going to create a plot with 4 subplots organized with 2 rows and 2 columns. So essentially what we do for each of these models is first drawing the scatter plot of our x's and y's. So by doing plot chemical magnetic, we are plotting a scatter plot with the x and y observations. On top of the scatter plot, we want to overlay the regression curve that we have fitted. So what we do is that since L1 is the output of the linear model fitted, so the first model, what we can do is to extract the coefficients from L1. That's the estimated betas, the intercept and the slope for this particular linear model. And then we use this, plug in the corresponding A, which is the possible x value, and find out what is the predicted y hat, predicted y value. By doing lines A, y hat 1, we essentially plot the fitted line in this case. We impose that onto the scatter plot. For the subsequent ones, everything is quite similar. So we first do the scatter plot, and then we overlay the corresponding fitted curve. And here are the results. Here are 4 plots where each of them contains points of the scatter plots, where x-axis is the chemical measurement and y-axis is the magnetic measurement. So the scatter plots in these 4 subplots are the same, but the fitted lines are different. This is the fitted line for the linear model, the simple linear regression model. This is the fitted curve for the quadratic model, so model number 2. This is the one for candidate 3, the exponential model. And this is the fitted curve for the log-log model. One question you might ask is then which model does the best? Well, you might think, okay, so I can do this by examining the differences between the observed and fitted values. So if the observed values and the fitted values, so our y's and y hats are really close, then the model predicts it fits quite well to this data set. Well, that's a possibility, but this comparison is actually not fair because models differ in their complexity. Some models, such as our candidate 1, the simple linear model, is very simple. It only has 2 parameters that we need to estimate, beta 0 and beta 1. For example, some of the other models, such as the quadratic model, we are including an additional quadratic term and need to estimate an additional beta parameter. If you ignore model complexity in model selection, it can usually lead to overfitting. That is, the complex model fits really well on the data that you trained the model with. However, for new observations, it does terribly. So an alternative to this is using leave one out cross-validation. Specifically, for each I between 1 and n, we fit the model with n-1 observations excluding xi and yi. So we leave one out and fit the regression. Then, using the fitted model, we predict yi, which is the ith observation we have left out. The prediction is denoted by y hat of I, and this can be obtained based on the estimated model parameters and xi. This can provide us an idea on how well the model will predict future observations. If yi and y hat of I are very close, and we didn't use yi and xi for fitting the model, it means that this observation is predicted quite well. Then LOCV selects the model with the lowest MSE on the left out samples. So here's the details on the procedures. For each I between 1 and n, we fit the model with n-1 samples excluding xi and 1i, and we obtain the regression coefficient estimates, that is the beta hats. Then we can compute the prediction by plugging in the beta hats and the xi into the regression equation, the regression model. And this allows us to obtain y hat I, which is the predicted value on the ith observation. Then we can compute the prediction error ei, which is given by the difference between the yi, the observed value on the ith sample, minus the fitted value predicted using the leave one out regression. The MSE of prediction can be estimated by the sample mean of the EI squared, so the squared prediction errors. So let's write the R code for doing this. What we're going to do is to loop over I from 1 through n, and we're going to store the EIs for each I. So the yi minus yi hats. We're going to store them in vectors of length n, and the E1, E2, E3, and E4 here corresponds to the E's that we obtained from each of the 4 models. So here's the code for this. It's a little bit hard to read because I tried to fit everything onto the same page. However, I will explain it a little bit. Essentially, what this does is looping over all possible k's or possible i's, that is ranging from 1 through n. For each k, we leave out the kth observation, and then we fit the regression model, for example, J1, the linear model, J2, the quadratic model, J3, the exponential model, and J4, the log-log model, using y and x, leaving out the kth observation. And then E1 of k, which is the residual or the error computed for the kth observation, will be the observed value on the kth observed value minus y hat, which is the estimate, the prediction based on the particular model by plugging in x in the kth x. So this is essentially the difference between yi and y hat of I. And we do this for each of the possible models. And here are the results we get on the LOCV MSEs, or we call them the leave one out cross-validation errors. These are essentially the mean of the square of the EI vectors. So you can see that for the linear model, the LOCV MSE is around 19 point something. The quadratic model resulted in a lower cross-validation error of around 17.85. And for the other two models, the exponential and the log-log model, the errors were a bit larger than the quadratic case. So based on these results, it tells us that the quadratic model was preferred using LOCV. In other words, it resulted in the lowest LOCV error. What is going to be on the subsequent two slides is not something that's particularly related to this course. However, whenever you do linear regressions, you should check some model assumptions and see the degree to which they are satisfied. So for a linear regression model, you have some common assumptions such as linearity. So the linear model that you assume is actually indeed the model for the data. The normality of the e's, the error terms, so they should be normally distributed with mean 0 and standard deviation of sigma, and that standard deviation should be the same for all of the observations. And you also want them to be independent, the error terms to be independent. So one way to check these assumptions is using a plot for the residuals and the fitted values. So if you plot the residuals, which are the e's, so you can also get it from the res object in the L2 output. If you plot this against the fitted values, your y hats, and you include a line at y equals 0, then ideally, if these assumptions are satisfied, then your fitted, the plot that you get, the scatter plot you get of the residuals versus the fitted values should look like there are no patterns. So they should be evenly distributed across the y equals 0 line, and there shouldn't be like a very obvious pattern. So in this case, we can see that this tends to be the case where the maybe our assumptions are well satisfied. Another thing you can do is to check the normality of the residuals. So we have discussed this in our first 2 weeks when we discussed how we can use QQ-plot to check the agreement between the theoretical and the observed quantiles. So in this case, we can check whether the residuals are normally distributed, or do they look at? So in this case, we plot the sample quantiles versus the normal theoretical quantiles. It appears that the points are very close to a straight line. So it indicates that we can say that the normality assumption is not particularly violated. This concludes our discussion of resampling methods. You can see that they provide a key tool to modern statistics. For example, if you're interested in hypothesis testing, constructing confidence intervals, or approximating the bias and standard error of estimators, and in machine learning or statistical learning, where you're interested in model selection and estimating the errors. One question you might have is, when should I use Bootstrap versus Jackknife? In general, Bootstrap is a more general method that allows approximating the sampling distribution of a statistic. So this goes beyond what Jackknife can do for estimating the bias or standard error of an estimator. In addition, as we have mentioned, Jackknife is not suitable when the estimator theta hat is not a smooth statistic. For example, you shouldn't use it for the sample mean, which is not a smooth function. So the sample median. So that's the 50th percentile of your sample. Jackknife tends to be more suitable for bias or standard error estimation when your n is small. So when you don't have a lot of data, and if your data set is quite small, and if your assumptions, so if theta hat is indeed a smooth statistic, and you're interested in the bias in SE, then maybe you can use Jackknife. One other thing that you want to note is the computational intensity of resampling procedures. As you can see, obtaining the Bootstrap and Jackknife replicates can be quite computationally intensive. In our in-class examples, for the sake of time, we have looked at cases when our n is quite small. So we played with sample sizes of, say, 100, 25, 10, etc. And these tend to be quite fast. However, for example, when your n gets large, and if your regression model is quite complex, and it takes a lot of time to fit the model, then fitting a model leaving out each eye, each observation, can be very computationally intensive. If you run this sequentially, so you do a for loop from 1 to n, then this might take forever. But the silver lining is that Jackknife and Bootstrap replicates can be parallelized. In other words, you don't have to use the for loop to run these. You can run each Bootstrap replicate or Jackknife replicate at the same time. So you can run many replicates on a cluster, so such as the Illinois campus cluster, at the same time. In this case, you can, for example, submit 1,000 jobs at the same time. And for each of them, you are leaving out one out of the 1,000 observations fitting the model. And because you're running them at the same time, you can get the results at the same time as well.